In parallel, there were some other fields that were developed: cybernetics, artificial neural networks, computational intelligence, a very popular field in the 90s. Its cornerstones being fuzzy logic, neural networks, and genetic algorithms, or evolutionary computation, the most general case of genetic algorithms. And also, machine learning was around as a term before it became popular. Pattern recognition is another related term. And also, data mining and knowledge discovery and databases. So, all these are fields that trying more or less to answer similar questions. So these fields evolved in parallel, and by Googling the term artificial intelligence, we can see, I Googled this term and I chose 3 random images, and we can see that there's still some confusion about what AI really is. So on one graph here on the left, we see that AI includes fuzzy logic and NLP and expert systems. In another graph, we see that it includes curated knowledge and data mining and reverse engineering the brain. And here we see that there's basically a set of concentric circles with deep learning at the center. So there are all these different approaches, and even nowadays, when the data-driven approach seems to be more dominant, there are people with many different opinions as to what we're really trying to do. And this difference exists for various reasons. First of all, there are really some conceptual differences between fields. For example, computational intelligence promoted the idea that we can recreate intelligence by mimicking natural processes, such as the process of evolution. There are also differences in the research background. For example, data mining was partly created in databases departments. And lastly, sometimes it's a case of marketing, right? So we saw that Geoff Hinton wanted to publish his research, he couldn't publish his research, and ended up coming up with a new term in order to find it easier to publish, that the term of deep learning. And now let's see some definitions of some of those fields, and this really makes things even more confusing. So when we go into the definition of computational intelligence from the 11th UK workshop on CI, I don't want you to read the whole thing, just focus on the bold words. You can see that this includes fuzzy systems, but also neural networks. And the definition also talks about learning and adaptation, things which are also in the domain of machine learning. And this makes us wonder, okay, so what are the differences between the fields? And then we see the definition of data mining, and this definition is really generic, right? It includes machine learning and databases and pattern recognition and statistics and AI, and makes you wonder what knowledge discovery in databases really is. Is it some kind of a superset of every AI-related discipline out there? It gets confusing. And it can get confusing even for the people who study this stuff, for the data scientists. This is a very popular textbook. It was the textbook to go, let's say, 20 years ago or so. I don't remember the exact publication date, by Christopher Bishop, called Pattern Recognition and Machine Learning. And the thing someone's going to ask is, all right, so what are the differences between the two? And finally, we have other subfields, other buzzwords. So we have natural language processing, referring to applications of machine learning on language, which sometimes is branded as something completely different. Recommender systems. Also, the term predictive analytics is thrown around a lot, which is not really a subdiscipline. Is basically an application. It means you're developing models to predict things in the future. But sometimes this is thrown around as if it is some kind of a different discipline as well. And this can get very confusing, right? It can get very confusing. You have all these fields with different philosophies, however, they're similar at the same time. And really, if someone wants to understand how all this came to be, they have to go through a presentation like this one. And it's not really easy to sell that way. So people came up with the word data science, the term data science, for that very purpose. Data science is an umbrella term that says, do things with data. It doesn't matter whether you're a statistician, whether you have a PhD in machine learning, whether you have a PhD in data mining or whatever. It means to do stuff with data. And however, there might still be a bit of confusion around data engineering, databases, data analysts, but I think this is clearing out. So now a data scientist is more or less considered someone who works with data, but is mainly focused on analyzing data and has some kind of advanced training in this field, such as a PhD in machine learning or a master's in stats. Also, now a data engineer is considered someone who works with mainly big data infrastructures, so they help design and maintain these systems. And big data is another buzzword. I say it's a buzzword because what's considered big data now might not be considered big data in the future, but okay, it is what it is, and this refers mainly to data that have the 3 V's, right? High volume, velocity, and variety. And traditional database architectures cannot really handle this, so maybe we need to go towards NoSQL solutions. So what does a data scientist need to know? So data scientists usually come from different backgrounds. You have statisticians who sometimes dislike going by the name of data scientist because statistics have been the oldest kid of the block of data analysis, so they don't like the term data science taking over. You have people from computer science who studied machine learning, either in the MSc or PhD level, and people from other disciplines, such as physics. And will then convert it, they learn how to use some tools. Sometimes they study a lot and they actually manage to do a full conversion. So this is a history recap of all the things we've seen. Statistics, as I mentioned, is the first field of data analysis with a focus on transparency methodology and math. Very, very powerful if you know when and where to apply it. The early AI approach, which is now called classic AI or good old-fashioned AI or symbolic AI, is not around that much anymore. However, it gave birth to many useful tools, some of which are still really used, especially around automated planning. And then we had many different disciplines around data and learning from data showing up, with machine learning being the dominant one. And this is not the dominant approach. This bottom-up approach, learning from data. However, a few more points before we finish with this presentation. The boundaries are fuzzy, so this is something I'd like to say. And this means that the different disciplines have borrowed tools from each other, so the boundaries are not that hard. For example, some tools from disciplines which are not very popular anymore must still be used. So you might find fuzzy logic being used in control systems and might be used in washing machines, for example. It's not as popular anymore, partly because there's not much left to research, but as a tool it works fine. Also, we find techniques from different fields other than machine learning being used in machine learning. So, for example, genetic algorithms, which is considered one of the cornerstones of computational intelligence, is used in machine learning sometimes to optimize neural networks. Also, some terms, some conferences are still very popular, even if the fields themselves are not. So, the KDD conference, Knowledge Discovery in Databases, it was one of the biggest conferences in the field. However, most of the papers and the people you see there, they do more like machine learning research nowadays. So they might not deal with the questions the data mining and KDD community tried to solve back then, let's say 20, 30 years ago. However, the term at the conference is still around. And finally, life moves in circles. So sometimes ideas fall in and out of fashion, and the reason they fall out of fashion is not that they don't work, just random reasons related to society and the people themselves. So, for example, genetic algorithms is a very powerful technique, which was overhyped in the 90s. And then it fell out of fashion, and now it's doing a comeback as a method to train neural networks. And we see this happening again and again, right? So some techniques fall out of fashion, and then they come in fashion. And this goes back into what I mentioned earlier, that what we should care about is the tools. And we just need to find the right tool for the job. So key takeaways from this lecture: statistics, mathematically and methodologically sound, and good when transparency is important, but not so good for when we care about predictions. Machine learning, amazing for predictions, good when lots of data is available, not so good in terms of transparency. Classic AI is not really around anymore. However, it was useful for the scientific progress we made through AI in cognitive science. Some things such as automated planning through AI are still around. And finally, very important, the AI vision is not complete, the mission is not accomplished, and we can see some versions of this vision of creating more general purpose AI machines in domains such as autonomous vehicles that try to combine many different modalities, many different functions together to create a machine that is really more than the sum of its parts. So other fields which I mentioned, you can just more or less ignore them, treat them as special cases of the above. And these days, the data-driven approach is the dominant approach, and the future lies towards general artificial intelligence. That is accomplishing the vision of the AI forefathers.